Lesson 2.2 Explainer. A 200 kilogram weather rocket is loaded with 100 kilograms of fuel and fired straight up. It accelerates upwards at 30 meters per second squared for 30 seconds, then runs out of fuel. For this problem, we're going to ignore any air resistance, and we're going to try and find two things. What is the rocket's maximum altitude, and how long is the rocket in the air before hitting the ground? So the key concepts are velocity, acceleration, time, and g. G is being gravity, which we're going to be equal to 9.8. And so the velocity is the directional speed, acceleration is change in velocity over time, and our goals are to find the height and time. We'll use kinematic equations and split up the problem into different parts. The first part, we're going to find the height from when the rocket loses fuel, so the fuel is 0. And then part 2, we're going to find the height from when the rocket loses the fuel to when the velocity reaches 0. And then part 3, the time from takeoff to landing. Now, when I said that we're going to find the height from when it loses fuel to when velocity is 0, this is because we know that the rocket is accelerating for 30 seconds at 30 meters per second squared for the first 30 seconds. But after that, it's going to be affected by a negative acceleration, and then until eventually velocity will be 0. So it's going to keep going up even though it's no longer having a positive acceleration. So for part A, we want to find the distance and velocity from here to here. So we're going to use the kinematic equation to find this distance using our initial velocity, which is just 0 because that's at rest, and then plus 1/2 acceleration times time, acceleration being 30 seconds, and our time being 30 seconds, and that comes out to be 13,500 meters, so our distance from here to here is 13,500. Now, since we have this, we can find our velocity, which is at d1, which is going to be equal to velocity final is velocity initial squared plus 2 acceleration change in d. That comes out to our velocity here being 900 meters per second. And using our 900 meters per second, we could plug that into the initial velocity here to find the distance. So that we know this is going to be 0 because it's going to have a negative acceleration until it gets to the very peak of its trajectory. So using our kinematic equation, we can do the velocity final, which is equal to velocity initial, plus 2a change in d from before, which is 0 equals 900 plus 2, negative 9.8, because our acceleration is now going to be gravity, or 9.8 meters per second squared, and that will come out to 41,327, and we can, for the distance between d1 and d2, and we can just add those together to get our total change in distance, which is what is the rocket's maximum altitude, to get us 54,827. So for part B, we want to know how long is the rocket in the air before hitting the ground, and first we have to find, I wrote a little motion diagram here. We know that this is 30 seconds, but we have to find the time from when it gets negative acceleration to gets to the peak, and then the time from the peak to when it hits the ground. So to get from here to here, we're just going to use our initial velocity, which we got from the last problem, which was 900, plus our acceleration, which is negative 9.8. We'll get that to be t, and t is 92 seconds. And then for our time that it takes us to get down here, we're going to use our final distance equals our initial distance plus velocity initial time plus 1/2 acceleration times t squared. And we know that the distance here is 0, and this was from the last problem, 54,827. So we could plug that in to get t squared is equal to negative 54827 over 4.9. Get the square root of that, and that's 110 seconds. And then to get our total change in time, we just add 30 plus 92 plus 110 to get 230 seconds. Here, I drew some motion diagrams. You can see our velocity is increasing, and then our velocity is affected by the negative acceleration then here it's 0 at the peak, and then it goes to the bottom. See that there? I think a common problem that could come up when doing this is many people might want to stop after that 30 seconds when the fuel runs out and the acceleration changes to negative 9.8. I think a lot of people would want to say that was the peak, but we know that the rocket would keep moving, so we'd have to keep solving for that.